Okay, so my talk today, actually, before I start, we'll sort of have two topics. One is I'm going to try to cover recent developments in deep learning, and mostly based on questions that I've been having over the last couple of days. I'm going to try to tell you what deep learning is, what sort of factors have led to it becoming so hyped and popular and so on, what things you can do with it, things that you can't do with it, and also I will then tell you a little bit about my research, and that will be research. So that part is things that I think are really important that we need to address that will lead to big developments, but that at this stage we still don't know the solutions. So I'm hoping, especially for the students in the audience, that they will enjoy that part. So the first part will be for people who already have their companies and so on, and they just want to know how to get in the deep learning bandwagon. And the second part will be more geared towards students getting into the field and looking for good research problems. So what is deep learning? It is like playing with Lego. And when I say this, I don't mean playing like Lego with just a couple of techniques that are available to you. It's a lot more fun. It's playing like with thousands of pieces of software. And these pieces of software, or Lego pieces, are often called, in the deep learning jargon, modules or layers. We have many of these. You can pull them from the web. You can build new objects with these pieces, and then you can release them to the web or to your company cloud or whatever framework you're using. This is pretty much how Torch, TensorFlow, Caffe, and many other frameworks that have been put out there by a lot of companies. Amazon has a very nice one, too, for sparse deep learning. And they all sort of based on this idea that you can have thousands of engineers all working with the same software. And that's a very powerful framework that allows them to build all sorts of interesting things. And the sort of combinatorial approach where you reuse pieces, where you can test the pieces well, is robust, allows us to communicate pieces of software. It's also robust to communication. And the sort of combination allows you to create an infinite set of things out of finite means. So you have at your disposal a combinatorial way of solving problems. And when you're dealing with problems that are very hard, potentially combinatorial, the only way to attack them is through having combinatorial approaches. And I think that's one thing that deep learning gives you in many ways. Now, more concretely, this is what a module looks like. A module typically implements a function. This function f takes as an input x and produces an output z here. And it also uses derivative information in the opposite direction. So if you have a loss function, and most of deep learning is based on optimization. That's the framework that's used for inference. And the optimization is carried out using automatic differentiation or symbolic differentiation. In the case of reverse automatic differentiation, we get an algorithm called backpropagation. It's a subcase of automatic differentiation. There's many ways in which you could implement this. The synchronous way is the most popular, but I believe you could do this asynchronously. And I think over the next years, this sort of question of can we do backpropagation in a biologically plausible way is going to be answered. Or at least we're going to develop algorithms that have a very different nature, sort of more like an ADMM type algorithms, asynchronous type things. And so typically you compute two error signals. You compute the derivative of the error with respect to the input, and you compute the derivative of the error with respect to the parameters. If the module has parameters, some of these modules have parameters, some don't. They're just functions. So for example, for a traditional multi-layer perceptron, a classical neural network, instead of thinking of it like the textbooks would teach you, which is this sort of big neural network, and you end up with these pages and pages of equations that you've probably seen if you look at Simon Haken's book or Chris Bishop's book. And that's really not the way we do it in practice. The approach we use is an old approach that actually Jan LeCun has used for many years, which is modular. All you need to care about is designing the derivative of the module. When you build a software module, you specify which function it implements, and you need to specify the derivative function. And provided you've specified this in the module, you can release the module. And if you, in fact, are using symbolic differentiation, like several frameworks out there, then you don't even need to specify the derivative. That will be done automatically for you. So all you need to worry about is implementing a particular function that you think might be useful. Now, the beauty of these modules is if they respect the interface, you can group them. Like I've done here in this chain, I've taken several of these modules, also known as layers, and I've combined them in a sequence. Now, if you respect the interface, you can glue these. And moreover, I can take this whole set of L modules, I can draw this red box around them, and that itself is a module. So once I've learned this module, if I find this module is useful, I group this, I bind it, and I release this module back to the web. So now you have another module that does, in this case, an L-layer neural network. More importantly, the graphs need not be sequences like I am showing you here. The graphs can have arbitrary topology. They can be recurrent, and most software pieces now allow you for this. In fact, the graphs can sort of interact with memory. There's memory modules. There's modules that write to the world or that read from the world. So they've become very general. They're not just your modules as in traditional neural networks where you have, say, functions and matrix multiplications and so on, but you have a really wide range of modules available in these libraries. Now, the first neural network that changed things was this iconic convolutional neural network. Now, what a convolutional neural network does is it takes and here I'm showing you one called AlexNet that was used for the ImageNet competition in 2012. And what it does is it convolves a window of parameters over an image, as the figure indicates. And then after convolving these, and it can convolve several. So the depth of these cubes, as you go from left to right, is how many of these parameters you're convolving, how many of these windows you're convolving with the image. The image initially has depth 3 for your 3 channels, RGB. And each of these filters then sort of will go over the image. So it's looking for it's looking for something. So it might be looking for an edge in the image. Initially, they're random, but that's what they will learn. They will learn to capture things like edges. The reason why they do that is because we've studied image statistics for a long time. And we know that image statistics are actually quite heavy-tailed. So when you model, for example, histograms of images for natural statistics, you don't get a Gaussian histogram. You get a very peaked histogram and then a heavy tail. So the space of images that you will see is actually quite small. So it might, the rare things are there's many rare things, but their probability sort of becomes low. And there's just a few type of images that are very common. And that's, in fact, what allows us to do learning, is the fact that the natural statistics of real images are small, and that's what allows us to be able to see. Our brains would not function otherwise if the world was much more adversarial. Through the optic nerve, we have about less than 1 million pixels, I would say, roughly. And so if you have an image if you look at the space of images 1,000 by 1,000, I guess in 256, you'd have 256 to the power 1 million, and that, you don't get that many images in the world. And you don't because that's a higher number than the expected number of atoms in the universe, so you wouldn't be able to code them. But the space of images in the world is actually quite small. So we might be able to come up with a finite set of sufficient statistics that will allow us to model images. And these ConvNets are an attempt at that. And initially, before they became popular, this was one line of research, especially pursued by Apo Hivarinen. And he has a beautiful book called Natural Image Statistics it's about that. Now, these networks also then have operations like pooling, which is the pooling operation will be just looking for a scale invariance. So if you have 4 things coming in, you pick the highest. So you try to do summarization, sort of a blurring operation as you proceed. They have nonlinearities, either sigmoids or many other functions, rectified linear units that are sort of these piecewise functions which are sparse. So the outputs of these networks in between layers tend to be very sparse. The activations are themselves sparse. And then eventually, after doing all these local pooling, pooling and convolution operations, which are aimed at essentially getting location invariance, scale invariance, illuminance invariance, and so on, you then need some sort of global transformation so that you do recognition based on the global image as well. So at the end, we tend to find these fully connected layers, also known as multi-layer perceptrons in these networks. That's AlexNet. And in fact, to this day, AlexNet, these typical architectures are still widely used. They were initially inspired by experiments from Hubble and Wiesel. And last year, I had the pleasure of having a couple of beers with the creator of the new cognitron in Japan, Professor Fukushima. And he was the first one that built this model architecture. Later, Jan LeCun brought something very important, automatic differentiation, which was what enabled you to fit these models to data. But originally, Professor Jan LeCun was working in a lab that involved neuroscientists and people working in tech. You know, the heyday of technology in Japan, when things used to be big in Japan. And he put together, by working with neuroscientists and in this next door, basically, he looked at the experiments of Hubble and Wiesel, and he tells me that this is what sort of inspired him, and how he built the new cognitron. And I've talked to Jan, and Jan was aware of this model, and this also inspired him and brought us here. Now, all these sort of things like invariance, you know, the ideas of invariance, the ideas of natural image statistics were explored for many years, and especially over the last 15 years at the Canadian Institute for Advanced Research in a program that was put together by Professor Hinton. And David Lowe, who gave us SIFT features, some of you probably still remember those, was part of that program. And so the fact that David Lowe succeeded with SIFT was actually gave us hope that we could succeed with ConvNets, that we could actually learn. And in fact, David Lowe, even though he hard-coded the same type of transformations to produce SIFT, he was a strong believer in that we should be learning all of everything that he had hard-coded by hand. Now, when things really mattered was in 2012, because two things happened in 2000, I guess leading to 2012, starting around 2010. One was we started using GPUs in machine learning, and it allows us to build very large models and to train these very large models. The other thing is data became available to train the models. And in particular, this data set that we're talking about here was the ImageNet data set. Although in parallel, the same developments were happening with the same models in speech. And in fact, Lee Deng, who's sitting here, was one of the people who worked on the speech efforts. Now, computer vision people had throughout 2010, 2011, and prior to that, been working on systems to do object recognition. These were extremely heavily engineered systems. You basically would throw all of computer vision at these models and at these data sets and hope that you would do better. And they were kind of caught in the same game that speech was playing, heavy engineering, and then let's lower the error rate by a little bit every year. And if we keep doing this, we'll eventually solve speech recognition and object recognition and so on. But then came the ConvNet, and that wasn't just a small reduction. That was that reduction that I'm showing you there in 2012. That was boom. That was a massive reduction. It took everyone by surprise in computer vision. And then some people started trying to figure out what are these Boltzmann machines, what is all this stuff, what matters? Because there was a lot of noise. There were a lot of things that worked well, a lot of things that didn't. This ConvNet seems to be the thing that's working well. But it took a little bit of time for the computer vision community to catch up. And in fact, a year later, in 2003, Matt Ziegler of Clarify, at the time he was a student at NYU with Rob Fergus, he came up with a model that, again, led to a significant improvement. And from that point, the vision guys were like, whoa, 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 we need to pay attention to this. This is for real. That wasn't just a fluke. There is something here. We need to start using ConvNet. And indeed, Andrew Zisserman, one of the top computer vision people in the world, with 3 Mark prizes in his belt and so on, was very quickly to catch up. And with Karen Simonian, they released VGG in 2014, and that was, again, a significant improvement that was almost as good as human performance. And since then, there's been so much work in trying to improve this. Most recently, residual networks of Microsoft effort, which is starting to show that we can match, in this particular task, human performance. This does not mean that object recognition is being solved, although people were so impressed with the results that they were, even vision people were saying that. But it means that for these very challenging tasks, we can now match human performance. And of course, much bigger systems have been trained by companies to understand images on the web and to understand how many people are in the image and so on. And people are trying to count calories from food photos and doing all sorts of interesting things with these models. Over the last few years, the revolution, going back to Lego, has been one of let's put more pieces of Lego one on top of the other. And the more you put, typically, the better the results get. And that's what it comes down to. The more GPUs you have, the more likely you are to win one of these competitions. But folks have also got quite smart, because what happens when you start putting many systems one after the other, and you rely on differentiation, is you have the chain rule, you have a product of Jacobian matrices, and that product can eventually either blow up or go to 0. If you look at the eigenvalues of this, you kind of want to keep the eigenvalues around 1 so that things don't blow up. And so for this reason, they introduced in residualness, they introduced these skip connections that I'm showing there on the rightmost of the image, of the slide. These skip connections allowed information to propagate. But the story is a bit more complex than that, I believe. Because if you look at here, something that's called a fractal net, you have this sort of sequence. And if you zoom in a particular block, like block 3 in this case, you'll find that that module itself is a module that has sort of these sort of hierarchical skips, where in some cases, in some paths, you have to do lots of computations. And you should think of the application of a layer as a computation. In fact, as these models start getting millions of steps, not millions, we're not there, but thousands of steps, you can think of each of these steps as the application of an operation, as you're running an algorithm and you're applying a transformation. And in fact, when these parameters are shared, that is when each layer layers have the same parameters, you can think of this as an iterative algorithm. So neural networks are essentially implementing many different types of algorithms. But instead of you relying on engineers, scientists to design these algorithms are learned from data. What you do is you create a structure. And then once you have the structure, like a ConvNet structure, you can fit them to any type of data. So instead of heavy engineering for speech and heavy engineering for vision in 2 different ways, you create a model that has the same inductive biases, like invariance, natural statistics, and so on. And that same model structure, those same inductive biases can be used to train the model either in speech or in haptic data or in vision data, and automatically learn a model that will perform well and do a wide range of tasks. As we see here in this sort of multiple thread type architecture, what these models are starting to do is, in fact, consider sort of multiple stages of computation. Consider doing things in a fast way, taking several steps of computation. There are these green boxes there, which are aggregators. They might choose which path of computation is the one that's most useful. There might just be gating, and then just pick one that was, so you're constructing the algorithm, basically. You're learning the algorithm as you go. Recently, there was a paper that actually did very well on several data sets, and it again uses the same idea. So it has this sort of nested skipping. And in fact, even the Google networks, like Inception, they also had a lot more structure than just a single linear chain. And in fact, in between computation steps, in between these layers, you would even inject observation information to sort of update the method. In fact, it seems that these methods are starting to look at multiple hypotheses and weighing these hypotheses with some data and selecting the fittest hypothesis to eventually generate an output. And this, in fact, reminds me a lot of some work that I used to do like 15 years ago, particle filters, where you're sort of implementing them with neural networks. Another network, besides the ConvNet, that has been very influential is the recurrent neural network. And out of these recurrent neural networks, the ones with called LSTMs, which have internal memory, which were also inspired by looking at cells and cell memory, have been extremely influential in speech and language. So a recurrent net, you can look at it in two different ways, like in this figure. On the left-hand side, you can think of it, you have an input X. That input X then goes into a neural network, and there's sort of, in this case, there's just one neuron there. It has some internal state, and then that state evolves over time. And the matrix W sort of tells you how that is the parameter of that evolution over time. So we now have a dynamical system, and then you also can read the state through a transformation which has parameters V and produces an output. Now, instead of a single neuron there, you could have a whole group of neurons there. You could have, in fact, a whole neural network with arbitrary topology following dynamics. And I'm going to show you soon some examples. Now, what we can also, another way to visualize this network is to do this operation called unrolling or unfolding, which is you just expand the network over different time steps. And here I'm showing you 3 time steps from t-1 to t+1. And you can see how this is sort of evolving over time. And this is what basically you see when you look at these models, these sequence-to-sequence models that we've been talking about for, especially in yesterday's session. I saw this picture several times. In a sequence-to-sequence model, you see this unrolled RNN. You have some input sequence, like in this case, a sequence in English, the cat sat. You feed in each word into the RNN, and then eventually, when you get to the word sat, the RNN cell encodes the information about the entire sentence, and you pass that information to what people call a decoder RNN. So the first part is sort of, the blue one is called an encoder. When you go to the orange, you have a decoder, and that translates to the French le chat s'assit. Yesterday, we also saw many people, even for queries, for ad matching and so on, they started doing these attention models. And in an attention model, in addition to doing just the LSTM and relying on that bottleneck to pass of the encoder to pass the state entirely to the decoder, what folks do is they run first the algorithm forward or forward-backward, and the 2-stage LSTM. And then they compute attention masks. They look, for example, if they want to read the output out of H9. And here, by the way, in this particular case, the task is you're given a premise, like in this case, a wedding party taking pictures, and you get a hypothesis, like someone got married. And then your task is to read from H9 whether the hypothesis contradicts the premise or whether the premise entails the hypothesis. But it helps instead of just using the information that was carried by C5 from the encoder, it helps to then, once you get to the end, to look at all the past information again and use that to get an attention gate that decides which of all the past information is more relevant. And then you use that to weight, in this case, H1 to H5 and H9 to produce an output. I'm sort of going over this very quickly, but I recommend this paper of Tim Brooke-Taschel for a lot of details on the actual equations. And this allows them to do things like, if you have a sentence that says, a boy rides on a camel in a crowded area while taking on his cell phone, and if the hypothesis a boy is riding an animal, the network predicts that this is an entailment correctly. If you have a sentence like a young girl wearing a pink coat plays with a yellow toy golf club, and the hypothesis is a girl is wearing a blue jacket, the network correctly predicts that this is a contradiction. Moreover, the network is able, as shown by the words in bold, is able to decide which words were the relevant words in reaching that decision. So you can sort of introspect a bit into the model. And yesterday, some researchers from Microsoft were looking at queries and introspecting into the queries and trying to figure out which are the words in this query that are sort of important about the matching to this particular ad. Now, attention is already where we're starting to depart from the typical networks. And then we've been departing a lot over the last 2 years. So when we look at this network here from folks at Facebook, and NYU, they're trying to do here question answering. So you have a question X, and then the output in red is a set of answers. And there's a lot in the slide, but basically, given the question, you embed the question, but you also take a whole knowledge base. Instead of just trying to have an LSTM that goes sequence to sequence. And yesterday we saw that framework is actually quite powerful. It's been very powerful for translation. And we saw that it's possible to reply to emails just by using a sequence-to-sequence model. But it would also be nice to ground this on a database, to ground this on a database or an image or the real world, to ground the discussion on facts or on your episodic experiences in the world. And so if you have a big database, what these folks do is they embed the knowledge. So they're using standard machine learning sort of embedding techniques, deep learning techniques. And then they embed the question as well. And in this particular case, they're using a key value database. And so you take the question, you find a dot product with all the sort of information that exists on the web. This could be an embedding of Wikipedia. And then they retrieve the keys and the values. They retrieve the information that might be relevant to answering the question. And that's basically the keys in blue and the values in yellow. So you go to the database, you retrieve the relevant information. And once you've done that, now you've gone from the big semantic memory to a working memory, which are just these vectors in blue and yellow. And then you use attention so you take the dot product between the question embedding and all those key embeddings to produce an attention vector, shown there by the green boxes. And then you weight the values using that attention mask. And you can then go back and do this several times. So you're doing reasoning. You sort of you've pulled a bunch of, say, web pages. I'm going to look at this web page, but I need to answer a question like, who is the president of the United States that was born in a state that Obama didn't visit in 2013. So you need to sort of have several pieces of knowledge to answer that question. And you sort of go through the cycle several times, and eventually you sort of output a set of candidate answers. But the key thing here is that this memory could be a semantic memory. It could be any database. And I think this is very relevant for folks doing business here. If you have databases, and you want to be able to interact with those databases as part of building dialogue systems or question answering systems or trying to generate predictions, this is a way of combining non-parametric methods where you have a lot of data with these very parametric methods where you're learning how to query into the database and how to produce answers. And this memory could also be episodic. And by episodic, I mean you could be monitoring a customer, and if you are following what this customer has been doing over the last few interactions, and you could follow what's trending right now, it's those experiences that you should be using to predict what sort of product to offer next or so. Another interesting, and you can even decide how to write to these memories, and that's what this thing here on the right does, the neural Turing machine, a project of Alex Graves. The paper is currently on archive. And he trains this machine to read and write to a memory and learns the memory. And in this case, it's learned the task of copying a pattern. And as you can see, it's very systematic over how it goes over the memory. So simple algorithms can be learned with this machine. On the left-hand side, I'm showing yet another example of attention, where in this case, I'm trying to sort of emphasize the point that it doesn't matter what the data is data. You can look at an image, you can use an image to compute attention masks as well, and then that sort of reweights which parts of an image you look at to produce a sentence. And these captioning models, which are essentially translation models, going from images to words is the same as translating, have become quite popular. Now, if you love probability, do not despair, because these models can be probabilistic. You can very well have modules that have noise as input, and for a very large class of distributions, you can essentially do Bayesian statistics and variational methods and so on, as part of doing deep learning. So here we're on the left-hand side, that picture is a variational encoder, and what it does, it's an unsupervised learning technique that takes an input X, an image, say, and it tries to compute the probability of some latent embeddings, Q of Z given X. And then you can draw a sample from this distribution. That sample is Z, so it's a noisy variable. And then you can use a decoder to compute the probability of an image given that latent vector. So this is pretty much how we do, like if you have a cloud, an ellipse of points, you can estimate the mean and the variance of that cloud. And once you have the mean and the variance of that cloud, you can use those parameters, those statistics, to generate a lot of data, a lot of clouds. And all those clouds that you generate would look like the original cloud. So if you capture the statistics of images, you can generate images. And that's what's shown on the right-hand side. Those are images generated by a recurrent version of these autoencoders called draw. And these are digits that are imagined by the model. So these digits don't exist in the world. And the models are not only, researchers are getting more ambitious. So we know we can capture the natural statistics of digits. Can we hope to capture the natural statistics of images in general? And this is a very hot research area right now. So in addition to probabilistic methods, Ian Goodfellow introduced a very interesting approach called generative adversarial networks. And then the idea there is you have two networks. You have a generator network and a discriminator network. The generator will try to generate an image, and the job of the discriminator is to tell apart whether the generated image is a real image or a fake image. So the discriminator is trying to tell apart fake from real, and the generator is trying to fool the discriminator. So they're playing a game against each other. And as part of doing this, the generator is learning how to generate images. The discriminator is teaching. So now we get into machine teaching, not just machine learning. The discriminator is actually, you're learning a loss, or you're teaching the generator how to generate better images. In this example here, which I took from Scott Reed, he will be presenting this at NIPS, he takes a sentence, he does this in a conditional way. He takes a sentence, in this case, a red bird with a black face, and he takes a location in the image, and also samples some noise, a noise vector Z, and from that, and doing sort of many modules of convolutions and so on, and upsampling, tries to generate an image. And then uses, again, a convolutional type neural network to produce an answer that, yes, it's real or it's fake. And when he does that, these are the kind of images that he's able to generate. For the first example, given the words, this bird has a black head, a long orange beak, and yellow body, I'm showing you first the ground truth. That's an image that actually does exist in the database. But the rest of the images, these are the figments of the imagination of the model. The model is capable of imagining these images. I think people are starting to get used to these results. But 10 years ago, when we used to generate images, they looked like noise. They were little blobs. And if you saw an edge there, you would get all excited and you go like, there's the gabor, and so on. And I remember Jeff and so on at CIF are getting all excited about this. We're getting there. We're generating. There's still a lot of things to do, and I'm going to go into those soon, but the field has progressed a lot. And again, very modular. As you've seen, this neural network is not just your standard neural network, but what Scott is a master of putting together many modules to synthesize these sort of complex architectures that allow him to get these good results. And he also can condition, he can draw a blue box, and he can move the bird around and so on. So you have control over your imagination. Now, a big part of this, too, is that if you look at researchers working in teams doing deep learning, to my annoyance, a lot of them have given up on doing math. I'm a big fan of, I've for over 15 years been teaching my machine learning course, throwing a lot of math at it because I think the principles are important. I still do. I still recommend you learn your math properly. But one thing that's interesting is that the neural networks, because they're implementing these arbitrary algorithms, they're also basically doing the arbitrary mathematical operations. So they've kind of relaxed the onus on people to do mathematics, or at least the developers don't have that onus, and they're more focusing on how can they build neural networks in interesting ways. Of course, the mathematical intuition sometimes helps you. Here's an example, and this example is on the Atari, is for learning how to control Atari agents. So initially, people were using these convolutional neural networks, no pooling in this case because of the type of images, just convolutions. And then the original networks, what they were trying to output was given an input image with a little video of a sequence of video frames, which we call the state or the observation. You would try to compute the value of each action, and that's the output red box there, would be the value of each action. And in this case, the actions would be the actions of the joystick. I don't know, left, right, up, down, press different buttons. There would be like, say, 10 actions, and you have 10 outputs. And whichever is the highest, that's the action you take in the world. And then in reinforcement learning, there's the composition, and this is of the value of a state and an action, the Q function, into two things called the value function, which is just the value of being in a particular state, and something called the advantage function, which is zero mean, and it just tells you whether one action is preferable to another action. Basically, it tells you when to act. And so we thought by creating these decompositions, we could do better, and we created this new module, which is essentially that green Y that you see on the screen. This didn't work well for, I'm not going to go into the reasons, but we started manipulating the graph, the neural network, to come up with a new equation. And this one worked well. Many people have tried to do these advantage learning algorithms before, but it's when we started actually dealing with equations, not through the mathematics, but through the graph constructs, that we were able to actually get some good performance. And in this case, I'm showing a video here of the network playing a game called Enduro, and essentially has to drive and avoid cars. That red thing is the derivative of, on the left, the derivative of the value with respect to the input, and on the right, the derivative of the advantage stream, the bottom stream, with respect to the input. So when you drive, it's valuable to look at the road. That's, the network learns to attend. Convolutional networks have attention inside of them already when you train them well. They learn where to attend. They pay attention to the score because that's what determines performance. This is an RL setup. And attention, and then, advantage on the other hand, it only matters, you only pay attention when there's a car in front of you. Because if you're driving and there's no cars in front of you, you can go a bit to the left, you can go a bit to the right. It has no influence on whether you survive or not. But if there's cars immediately in front of you or pedestrians, then taking action is really important. And of course, we do this not just for one game. We do this for 57 games. The games are very diverse. And the same agent is launched to play all these games, the same network architecture, although mostly with different parameters in this case. And when you compare what these networks do, for example, in Atari with eye-gazing data, they actually you tend to see similar patterns. I haven't done a systematic study, but I have looked at what humans pay attention to, like look ahead, like looking at where the capsules are, where the ghosts are. And this attention can be local, it sometimes can be global. You search for ghosts all over the image. Now, one thing I want to tell you here is that we've been working a lot on these Atari games as a way of building better agents. And there's been a huge amount of progress that is not just computation, but it's actually algorithm development, designing better networks and designing better algorithms. The thing that was published in Nature like last year, I think, I think it was only last year or 2 years ago, is that line at the bottom. So I'm showing you here steps, as in environmental queries versus like performance with respect to a human who's actually an expert game player. And you can see this, the improvements over the last few years with using different frameworks has been vast. And the same networks, in this case, is a network that we call the dueling architecture, which is currently state-of-the-art on Atari, can also be used to control. So in this case, moving an arm to a target or controlling this fish to swim to a particular target. So you can do both continuous control and discrete reinforcement learning. Now, continuous control is important because we've also been building networks now that start having multiple columns. And so in this example, there's a first column that's trained in the lab for a robot arm that's learning to catch. And you train the green network first. And once you've trained this green network, you use the features of the trained green network, and provided that the simulation is realistic, you can now train a second network that reuses the green network. And this network is much smaller, so it's much faster to train. Because on the real robot, you don't want to be doing too many trials. You don't want to break that arm. Whereas in the simulator, you can afford to do a lot more computation. So we are now also exploring ways in which we can transfer from these agents, these reinforcement learnings, to real environments. And this is necessitating, once again, the design of interesting network architectures, not just your typical convnets. So what I've told you up to now is that engineers are building these very complex models, that they're modular, easy to manipulate. These models reflect different types of inductive biases, different types of intuitions. And then behind the scenes, everything gets done with automatic differentiation. You don't need to even be thinking necessarily about how the learning happens. You just use one of the standard or SGD type algorithms that are provided to you. And so in thinking how this network does computation, you're sort of thinking about inference steps. So inference still is something that matters. And the deeper these networks, I've argued that the more computations you're doing. And at the end of the day, it's the data that decides what the algorithm will look like. So the idea is you tune algorithms to specific data sets as opposed to trying to design generic algorithms. But now I move from what exists right now to the field of dreams. So we're moving on to research, the second part of the talk. And we have to ask ourselves the following question. Could we just learn these modules? Can we solve the meta problem? Can we discover new models? Can we do knowledge discovery? And how do we reuse modules, these abstractions, to solve new solutions? And in effect, how can we learn to learn? How we can learn models that will then continue learning? Very much like when your baby is born, your baby learns a lot. It's a machine that's been learned through evolution to be able to learn. Now, compositionality is very useful. Intuitively, if you're cooking, you chop tomatoes. If you learn to chop tomatoes for one dish, that will likely be very useful if you have to chop tomatoes for another dish. So this sort of compositionality reuse is extremely important in motor control and in perception as well. Another example of the value of compositionality is I can ask you all to imagine a pink dragon with a yellow zebra on top. And most of you will have no trouble imagining that. If you do, let me know. Yeah, that'd be an interesting case. So in this case, I was like, actually, the yellow banana riding a bicycle came because I asked someone, imagine that, and he Googled it, and this is the image that came up. But a lot of things Google will not give you. So you have this combinatorial generation of images. If you have concepts of things, you can sort of create things with different properties and different relations. And this is something that's been known for many centuries. Already Humboldt referred to this interesting property that happens with DNA and with language, where you have a finite set of resources like DNA or in finite set of words, and you can combine these to generate a combinatorial variation. So this is, I think, the basis of creativity. I think this is what makes language so powerful. You can start from the grounded, like when a word refers to something, and we know how to learn grounding these days, but you can lift language, and you can write books, and you can plan the future, and you can talk about these, Game of Thrones and all these imaginary setups through the power of words, just by combining some discrete tokens. Humboldt called it the infinite use of finite media. And it's robust. And in fact, language exists because we have noisy communication channels, and it's robust to use discrete communication. And in addition, it sort of allows for this combinatorial creativity. And the same arguments can be said about DNA. Fisher, the statistician, was also obsessed about this question, incidentally. He wrote papers like wondering, why is it that DNA is discrete? Why is language discrete? I mean, there might be some latent embedding where this thing is continuous, but why is a word a thing? And there's been a lot of recent research trying to exploit compositionality. And one of these chains of work is probabilistic programming. I think well exemplified by a recent paper in Science of Brendan Lake and Josh Tenenbaum, which I recommend everyone to read. And what they do there is they try to understand these omniglot digits, which is a very large number of digits where you have very few data, you have very few examples. So it's the opposite of the typical deep learning setup. You have many examples, many sort of different symbols, and very few examples of each symbol. And they want to do things like learning to generate new ones or learning to recognize and a few other tasks. And what they do is they start with a few components or primitives, and then they learn how to glue these components to form parts, and they learn some relations that allow them to then form the digits. So they learn a generative model of the digits. They also have, actually, the data set consists of time traces of how the digit is drawn. So basically, by running a motor program, they produce an image. So there is this idea that a concept is represented as a program. There is a motor program that gives you this concept, which is the digit. And the way they do inference is, given an image, they try to infer through Bayes' rule and through probabilistic programming, they try to infer what is the program that generated this. And they use sampling to do this. In neural networks, there's been approaches like one that I'm going to tell you about soon, the NPI, but also this approach of Sebastian Riedel and Tim Rocktaschel and a few other collaborators, where they instead of trying to provide the primitives and learning the structure, what they do is they provide the structure of the code, and this is very much like when you provide the structure of the network, and then you learn a few lines of code. So this is like you go and learn the parameters. So you provide the structure of the code, the trace, and then you sort of learn the details of the functions that you call. And in fact, there's been some, just across the bay, Jacob Andreas and his colleagues have also been working on this sort of thing, like for question answering with images, where you take an image through a convnet, but if you have a question, you use a parser, like a standard parser, to choose the layout of the network. So it grabs a set of modules that are relevant to the question and assembles the neural network, and then uses that neural network to answer the question. So in this case, again, the way of constructing the structure is automatic. It's deterministic. Given this sort of parse, you decide what the network structure should be, then you train the model, you release the modules until the next question comes up. You build a different network, train it, and so on. And then the idea of doing this is you want to reduce sample complexity. Because if you have to solve a new task that requires that you reuse models that you had already learned in the past, you don't need to learn everything from scratch. You can reuse things, and that allows you to be a lot more data efficient. So a lot of folks are talking about one of the downsides of deep learning is that it requires a lot of data and so on. That is changing. A lot of research is going into how to make these methods sample efficient. We're not yet there, but that's kind of where a lot of the research is moving toward. And in addition, because you're reusing modules, if you've already learned a module and you don't want to sort of override what you've learned, by having less collisions here, by using different modules, you also allow yourself to have different type of knowledge. So you can your method can be more continual learning. You can learn a task, proceed to learn another task using the same architecture. Here's another example. So the idea is over time, here I'm showing you would have a sort of a set of modules, and if what you want is the network on the right, you could just have this very massive network, and you could just on the fly assemble through gating what this network should be. We still don't know how to do this well. This is a challenge. But there are examples out there that tells us this is important, and it's important also for computation. There is something called PAQ, which is the state-of-the-art in compression for Wikipedia. And what it does is it takes many inputs, so predictors, PPM-type models, which are like Pitman-York-type processes, and then it has a modular structure. And Matt Mahoney created this modular structure just for computation. So you have a block of, say, 256 units, and that's because you look at the most recent input, and you check which byte it is. If it's 3, then you select only neuron 3. All the other neurons don't act. And then you only learn a subset of those neurons. And this is extremely effective. Actually, Byron Knoll, one of my students, trained this on Kevin Murphy's latex code. And as you can see, it makes very good predictions. You type F, and then the rest is the model prediction. For example, consider the form of the exponential family, which is something you would say if you're Kevin Murphy. Or as the last one is my favorite, long live P of vector theta, and then the model says given data. This is peering into the mind of Kevin. Now, I'm going to tell you about 2 of my own works that I've been doing recently, which sort of aim at dealing with this compositionality and learning to learn. The first one is NPI. The idea of NPI is to have a network that does multiple stages of computation, but also can do recursion, and can learn not just one program like NTM, but it could learn many programs. So now I want to create this network that could learn many, many programs, and recursion will allow you to sort of do this sort of program reuse. So basically, given an input, in this case, basically a set of numbers in a particular configuration, a scratch pad, and given a program which I'm indicating by this orange bar, and you have several vectors, and these vectors will be the programs. Basically, in a neural network, the weights determine the program. Neural networks do transformations. So according to whichever weight you give to it, they will do another program. Likewise, you could also think you could code the program as an input into the neural network. So the input to the neural network sort of, you could pass 2 inputs to the neural network. One vector that determines which program it runs, and one vector that are the arguments. And this is effectively what we do here. And so the idea is you call a program, and then there's this NPI core that's basically a recurrent neural network, for example, an LSTM, and it does a set of operations, and then it stores its internals in a stack. So it has a prediction that says push to the stack. Then it chooses the next program, so it recurses down. It solves another operation, in this case, write the number 0. And then once it's done with that, it pops, and it returns control to the master program, and then the master program keeps carrying on. The hope is that given demonstrations of someone adding, in this toy example, you would, from those demonstrations, learn the program. So what we're targeting now is this is a new take on program induction. And there'll be a workshop at NIPS which will bring people from the classical program induction, the guys that try to infer formulas automatically for Excel, which are deployed with Microsoft products, as well as people from other fields, and certainly a lot of people from deep learning are looking at this now. Now, we started this last year by looking at the case when you don't learn this end-to-end in this manner. We're certainly after that. We're certainly trying to learn from low-level execution traces or end-to-end. But what I'm going to show you now is what happens if you take this memory of programs. And in this particular case, we used a key value representation for efficiency. And we're going to, for each of these modules in this neural programmer engine, we're going to provide labels. We're going to provide basically to the algorithm, instead of providing it with input-output labels, we're going to provide it with execution traces and essentially the code skeleton and allow the algorithm to fill in the details. And so we're going to provide data like which program to call next, whether the program should halt, and which arguments to pass to the next function. And then the algorithm will sort of run sequentially. So here's an example for addition where you first call a program that adds the first column. That in turn calls a carry program, an ACT program, which essentially adds that column. Then it returns control to the master one, which then calls a carry program, which has to move a pointer and eventually execute a number. So these networks, by the way, get very, very long. And here is a demonstration of it, adding numbers. It's moving these pointers automatically. And it's reusing, it's interacting with the environment with a scratch pad to decide which program to call next and with what arguments. And then it generates the code on the right-hand side. And code generation is extremely important. And I'll come back to that. And I mean, addition is kind of a silly thing. I mean, why train such a big beast to add numbers? There's much easier ways. But that's sort of a proof of concept, because I can now look at something more interesting, which takes as input actually a whole covenant of images, where the task might be given any image and given some desired orientation and elevation. I want to move that object to that particular orientation and elevation. So in this case, I want to move the cars. I'm given cars in arbitrary positions, and I want to move them to the front view. So again, you can work with these image features and do several steps of computation and take the car to that canonical view. Oops. Thank you, Microsoft. So let's hope the guys are back there. Hi. You're working on it? OK, cool. And so what the video will show you is that using cars that the network had never seen, it will learn to move those cars to that canonical view automatically. So that shows that it's capable of doing this statistical generalization, so it can generalize from arbitrary new images. But it's also able to do another type of generalization, which is the one that we really most intuitively think of generalization, which is this symbolic generalization. Yeah. So if you teach a kid to add numbers, like of length, you teach them how to add maybe 3 digits, one after the other. If you give them 10, they will have no trouble adding them. And in fact, if you write a piece of code that adds numbers, that symbolic piece of Python code, say, will be able to add those numbers. And so I think moving toward these discrete structures will be useful for that. Ultimately, what you want is networks that also generate code. Because if they're continuous dynamical systems can sort of accrue error over time, and you eventually have failure. But if you actually produce some sort of discrete plan, like a piece of code that tells you how to add numbers, this can generalize unboundedly. I mean, up to, provided the code is right, up to what the machine is capable of doing. OK, we're back online. Thank you. Okay, so that's, again, generating the code for the operations that it performs on the car to bring it to canonical view. And we've also done this for sorting. So here's some important results. You're able to learn to sort integers using only 8 examples. In a sequence-to-sequence model, you would need like thousands of examples. But if you reuse structure, your sample complexity goes down. And that's mainly because if you're learning to sort, you get to, even though you might only be given 8 instances of sequences of numbers and how you sorted them, you actually are given a lot of data for how to swap numbers. You know, the sub-functions that it calls, you get to see a lot of data. So reuse gives you the efficiency. Moreover, by using reuse, we get better generalization. So here the model is trained with sequences of up to length 20, and then we try to do this true generalization, which is not how well does it do in other sequences of length 20, but rather how well does it do in sequences of arbitrary length. And as you increase the length, you see that the traditional models will very quickly collapse. So these are the sequence-to-sequence models using translation introduced by Ilya Sutskever. Recently, which are extremely good for many tasks, but they don't have this type of generalization, whereas by having this sort of multiple recursion, you're able to go much further. And it eventually collapses because of the reasons I just told you when things failed. And you can do this for addition, and there it doesn't seem to collapse. It's an easier task. An important thing, every program that I've been running here uses the same network with exactly the same parameters. This is the same machine that's implementing all these programs. It's able to rotate images, to sort integers, to add integers, and it's the same network. Moreover, once you have that network, you can fix it, and you can decide to just learn the program vector. And you can learn a new program vector, for example, how to find the max of an array of integers. And it basically learns to call the program sort and then look at the rightmost entry. So it learns to learn new tasks. So this sort of attempt at which relies on using heavy supervision has shown us that it's possible to design models with low sample complexity that can sort of continue to learn, that can learn new programs after having learned some programs, that can solve many tasks with the same parameters, that can actually look at the environment and look at what it has done in the environment. The environment is memory, can be thought of as memory. I can do something in the environment and I can query the environment back. I mean, this is like how, you know, I remember phone numbers and so on. I look up at my phone. I don't remember even my phone number. For most things, I just ask my wife for help. And so I've learned to harness my environment to achieve. A lot of mind is external. It's able to continue learning. A learned model can already learn more. And the way it's taught is not end-to-end like input-output pairs. And I think we need to start thinking of ways of training models which is based on demonstrations, and we need to think of that more seriously and not just as framework of end-to-end. Because when you're end-to-end, for many tasks like semantic parsing or question answering, it's really hard to come up with input-output pairs. And people in dialogue and so on, people are struggling because they don't have data sets or natural language understanding. And rather, we need to sort of start seeing executions of how conversations happen and so on. Like the way children, I guess, learn in schools, the way they taught lessons and the sort of higher cognitive tasks. For low-level tasks, end-to-end is important, like basic motor control and so on. There's been some efforts, notably the neural programmers, neural GPUs, that are sort of being championed by Ilya, by Rob Fergus, Wojciech. And these also are very good works in this area. There's been actually an explosion over the last 2 years on the idea of learning programs. They don't have this compositionality that we exploit in NPI, but they try to go to end-to-end. So we're trying to sort of bring all these approaches now closer. But fundamentally, what you would like is not to provide traces. It still would be interesting just have these demonstrations and discover the programs. And discovering the programs is the same as in a convolutional network, discovering these groups of units that code for different parts of objects, like for eyes and mouths, and understand the entities and be able to reason with these entities. and to the extent that these entities are useful for solving tasks. This is the problem of knowledge discovery. This is a problem that this conference, one of the problems that this conference was set to solve. And we have focused a lot on data mining, but knowledge discovery is extremely important. And a lot of the future technology, I think it's going to be based on this, and being able to create these models that you can, really learn with very few data and can learn to do many things with them. I'm hoping there'll be a lot more of this. Finally, I'm going to briefly, I've been talking about learning algorithms, and when we train neural networks, we use algorithms to train neural networks. So then it begs the question, why not just use one of these neural networks to learn the algorithm that is used to learn a neural network? Learn to learn, and in fact, I've done this to 4 levels. Learn to learn to learn to learn. I'm going to go quickly over this example and then take some questions. So the idea is to use a neural network to learn another neural network. The intuition is as follows. When folks doing optimization, if you look at the field of optimization, depending on whether you look at deep learning or you look at sparse methods or you look at people doing meteorology, everyone has the sort of family of favorite algorithms that they like to use. And they craft these optimization algorithms so that they become very good in that domain. In general, at least we know for discrete spaces and combinatorial optimization, there is no optimization algorithm that solves all tasks. If you're going to do that, just use a random algorithm, because that's basically what the no-free lunch theorem tells us. So what folks are really doing is they're tuning by hand. They're hand engineering algorithms. So once again, just like we stopped hand engineering the networks to do recognition and speech, let's stop hand engineering the intuition here. Let's stop hand engineering the algorithms, and let's actually start learning algorithms, provided that you're in a domain where there's data. So if you have a class of problems where there is where for one particular instance there's a lot of data, you try to learn the algorithm for that instance, and then hopefully you will be able to generalize to other instances of that problem. And so in the typical algorithm in neural networks is gradient descent, where there is a new word that we've invented, the optimize Z, which is the thing that you're optimizing. Might have some parameters theta that's followed, you're updating by gradient descent. And then what we're going to do is now we're going to update them by using parameter updates generated by this other neural network that is the optimizer. And the optimizer is basically this function G, and it has parameters phi. And so we have these 2 recurrent networks going one next to the other, an optimized Z that's doing this sort of dynamics. Basically, recurrent networks are Turing complete. They can model any dynamics. So provided, of course, they might require lots of neurons and so on. So the interesting empirical question is, how can we engineer these networks to actually answer to model many dynamical systems, many physical systems like simulation, I think physics, we're going to see a lot of this in graphics too, as well as the dynamics of learning algorithms. And so here we have the optimizee doing the updates to the parameters, and we have the optimizer in this computational graph. And what we're going to do is actually an algorithm that sort of does coordinate ascent, where there is an LSTM optimizer for each parameter of the primary network, which has objective function f. When we do this with quadratic functions, and we've tried several versions of this, some that use second-order information like NTMs, those we haven't been able to get to work well in the stochastic case, and this sort of mirrors the results that also exist out there. But we also have these online methods, online SGD methods. And here, the learned algorithms do a lot better than the classical algorithms that are used in deep learning, like ADAM, RMS-prop, and so on. Moving to a more interesting example, using an MLP for digit recognition, we also noticed that the learned algorithm, the LSTM in red here, completely outperforms the other algorithms when you try it on different data sets from that same, from other data sets of digits. The interesting thing is you can change the number of optimization steps and it still wins. you can change the number of neurons of the network. So now I'm changing the class of problems to which I'm running the optimizer, and it still does a good job. I can add more layers, and it's comparable to the best algorithms that people have engineered over the years. And this is basically telling one story. If your job is to hand engineer optimizers for the MNIST data set, you should stop doing it because you're out of a job. You've been, and trust me, there were lots of papers that were basically using MNIST as an example for trying new optimization algorithms. Of course, it eventually fails. If we change the activations, if we move far away from the model class, it will fail, because the idea is we're trying to identify a narrow domain where we learn and we become good in that narrow domain. The idea is we're not trying to learn an optimizer that will work well in all problems. And we've done this for CIFAR, where we train with a subset of labels and then test with a different subset of labels. And once again, we outperform the other methods. We've done this for neural art, which is, I'll just very quickly go over this, but it's an optimization problem where you're given an image called a content image and a style image, which is, say, typically a painting, some art, like in this case, Van Gogh. And you try to sort of write, you want your pet to look kind of like a Van Gogh, to share it on Facebook or whatever with your friends. And every time you do this, you have to wait like 5 minutes or 20 minutes. You run an optimization problem. And so because this is a case where you keep doing optimization over and over, we wanted to sort of automate this with a neural network. And we're able to do better than the existing optimizers. And importantly, here as shown in this example, in terms of the degree of transfer, if I use a new content, but with the same training style and same resolution as in the training data, this seems to work. But even when I use completely new content, a completely new style, in this case a moon, and completely different type of resolution, this still works. I first gave this talk on the day of Brexit. And I looked at that image on the right, and that completely captured how I felt that day. So with that, I would like to conclude my talk, and hopefully we have some time for questions. Thank you very much.
This is a great talk. Yeah, I really enjoyed. So
thank you.
Going back to the first part of your talk where you showed the Atari game, and then you showed that the standard, this the output layer gets split into two parts, the Atari game slide.
Yes, yeah.
And you give some intuition as to why the split is going to do well, and also that led to a different way of designing the mapping function. And that was good intuition there. So I just wonder whether, maybe you can sort of elaborate on the intuition and also connect that example to the final part of your talk about learning to learn, to see whether that learning to learn can automatically recover the intuition.
Yes. So, so first intuition. So the idea is you want to learn the value of being in a state and an action. But for you to be a successful decision maker, you don't need to see the value of each possible action in each possible state. There are states of the world in which you encounter yourself where actions become irrelevant. You don't want, so in particular when you're driving, if there's no car in front of you, it becomes irrelevant whether you go a bit to the left or a bit to the right. If you're provided you're in the middle of the road, staring ahead, you're in a valuable situation. So you're in a good state of the world, which actions you take as with the steering wheel, that's sort of irrelevant. So it's not needed for you as a driver to be testing what happens when I go to the left, what happens when I go to the right. Maybe a novice driver would do that. But you typically, if you go to England and have to drive on the other side of the road, you're not going to be doing that very often. You're not going to be, what happens if I touch this English pedestrian a little bit? You will avoid those actions. Maybe you... And
then the second part, of course, is that whether that kind of thing can be automatically discovered through learning to learn.
So that particular structure, learning that structure is something that we can't do at present. Identifying that there is this important split. We created as inductive bias, and through some engineering, we figure out how to learn that model and to do better. But the question of completely discovering the structure of the network, That is open. There's some examples out there, but that's an open question.
Thank you. Maybe.
Thanks for a great talk. I can say unequivocally that I came into KDD not believing the hype, and I'm leaving saying I'm soon going to be out of a job, so I better get my hands on this neural net stuff. I wanted to ask you, particularly in the context of NPIs, but also in general, what advice would you give to somebody just coming into the field, looking at deep learning for the first time, and not wanting to be out of a job because it seems like your programming is all out of them?
Yeah.
Not just us, but everybody, basically.
Yeah, the intention is right, probably, is not to put everyone out of a job, but only the people who are doing irrelevant stuff. Like
But
testing
if
of
the neural nets are learning how to learn, we're all going to be relevant soon. So.
we still,
Sooner or later. Huh?
Yeah, we're still a long way off.
Right.
And of course, you know, like seriously, as a societal matter, this is an important thing. We need to be thinking of the value of jobs and how technology affects them. Although I think there's other societal factors that matter more. I can talk about it over beers.
Agreed, yeah.
But in terms of what someone should be looking at, Kevin Murphy will come up with a new edition of his book that will sort of reflect his more modern view. But at this point, I recommend, I'm going to self-promote here, look at my lecture notes online where I try to go into this, the modular approach to deep learning. Jan LeCun has excellent lectures online as well on this modular approach. I think Leon Butter might as well. I mean, certainly Leon was one of the initial people behind this. And then, you know, there's, I mean, look, basically, I would recommend look at what sort of top groups in deep learning are doing both in academia and at universities. So in academia, we still have great researchers like Joshua, Ruslan, and many others. Of course, Facebook, OpenAI, Google, and pretty much every company really is producing now really awesome papers. So iClear is a good conference where you can get the NIPS workshops, they're vast these days. But I think perhaps, at least my personal belief is if you know the models that I went over today, the attention models, different types of memory, how to attend to memory, read from memory. I covered supervised, unsupervised, and reinforcement learning setups, so the whole range of different learning paradigms. Going into the future, multi-agent is important. I mentioned communication. I didn't, because of time, go into communication, but there's a lot of effort now in how agents learn to communicate, how to interpret what the agents are doing. Generating programs is not that different from generating explanations, so that's sort of an area I think especially we would like, if we want to provide answers to you know, doctors and so on, that's why we made a decision, that's very important. Very large-scale reinforcement learning is difficult when you're outside a company. Some of these experiments with thousands of GPUs go on for a couple of weeks. I mean, that's, but the successes have been huge. There's Atari, there's these control programs, there's AlphaGo, and so on.
Of course. I'm from UMass, so yeah,
okay.
we were all cheering you on.
Okay, maybe.
But yeah, so I think there's all these things I mentioned, I think in my talk are worth looking into. A lot of them are open research problems at this stage.
Great, thanks a lot.
Okay, maybe let's move over to that.
Sorry, I
over
didn't
there.
see that huge line.
So I think we probably have time for maybe 3 full questions, and then maybe we can take the rest.
Thank you. It was lovely talk. You spoke mostly about applications which humans are fairly good at. And even the optimization problems, Atari, the RL, the action spaces are fairly small. Have you seen work in combinatorially hard problems, scheduling or difficult graph isomorphism? Is there a way, and you started learning to learn programs, but can we optimize discrete spaces which are pretty huge to search? And learning the structure of the space using a deep network, does that seem a promising direction?
Thank you for that question. That's a very good question. I think that if there's a discrete space that has inherently some sufficient statistics, or another way to express it, a latent continuous space, we can hope to do well in those type of setups. If you're dealing with with a problem that intrinsically is NP-hard, this is not going to solve it. If
But
you're
we
dealing
do-
with a
but we
very
do have
hard
heuristic-
combinatorial problem,
You have heuristic solutions even there.
so
Yeah.
you have heuristics, and so you could potentially sort of tune these approaches. I mean, in fact, that learning to learn that I talked about in the last slides, you could try to use that for combinatorial optimization. We haven't. But in a sense, once you train that optimizer, that LSTM optimizer, the other nice thing about it is you take it out, you can use it to optimize new problems, and there's 0 hyperparameters. You don't need to engineer anything. And so that kind of degree of the automation, which is kind of one of the things people are pursuing with Bayesian optimization, could potentially be done with these models. But we really have not. I think Oriol Vinyals was looking at traveling salesman problems and so on. We haven't had the same success. I think, again, unless there's some structure in the problems that we can exploit through differentiation, I don't think we will have much to contribute. And of course, ultimately, some problems are very hard, and we can't solve them.
Thank you.
But if we're talking about Cplex, I think we can. Yeah. We will one day take Cplex.
Take Cplex, that's good. Interesting. Thank you.
Okay, so maybe
Yeah, go ahead.
Jiming San from Georgia Tech. Awesome talk, very convincing as well. So in some of the policy making and decision making applications, such as diagnose disease, recommending drugs, you not only need an accurate algorithm, but also good intuitive explanation. And some of the attention model explains, sort of does that in the image domain. But when you talk about compose more and more complex logic together towards the end, what's your thought in terms of how do you interpret those complex decisions coming out of very complex composition of neural network models?
So this is still, like I said, it's an open problem. Attention, in fact, the layer that I showed there that does our attention is something called sparse max. And if you look at its mathematics, it's the same as mathematics of like projector gradient methods, like the type of methods I use in Lasso, for example. So they sort of start emerging also. In general, like being able to get interpretation is a challenge. There's a few papers out there trying to distill to decision trees or trying to sort of come up with explanations. Carlos Gestrin had recently a very nice paper on that. But this is an active area of research. I think we haven't solved that problem.
Okay, thank you. One last question. Sorry, this queue was just formed earlier, so I think that will be the last question of the session. I apologize, but
Thank you.
I will be available afterwards. You can ask me questions outside.
Thank you. I really enjoyed your talk, especially your example of showing that how to generate the infinite possibility from a finite set by doing literature, and at the same time you also show the human genome, which is also essentially just 4 types of base pairs that composes the whole universe of our human beings. And there is a lot of successful work done for documents, but on the biotech industry, a key problem we face is how to predict phenotype from genotype, which predicting phenotype with genotype, like predicting crop yield from the genetic makeup of the plant, for example. And it's the type of data is relatively high dimensional. You have 10 million possible SNPs, for example, for crop, and then the number of examples is relatively small. Do you see a possibility of extending deep learning to that area?
Potentially, maybe. It's not my area of expertise. Bioinformatics, I only know a little bit about it, so I really can't comment. I know there's a few folks looking at it. There's a few papers out there, but I haven't examined them myself, so I can't answer your question.
Thank you.
For now. Thank you very much.
so thank you very much again.